Okay, good morning, everyone. Hello. Welcome to the calculus class. And let's just start. Okay, we started the section 2 of chapter 4 last week, and let me briefly consider what we considered in this section. Okay, we want to consider the mean value theorem, which is important in mathematics. And actually, as you probably noticed, this theorem is used in several fields, especially in engineering departments. Now, before we consider some generalized mean value theorem, we want to consider the special case, the Rolge theorem. So it specifies as three hypotheses. First, the given function f is continuous on the closed interval from a to b, and it is differentiable between a and b, except these endpoints. And additionally, f of a and f of b are the same. That means you have the graph which is smooth, and the initial value and ending value are the same. So so if that's the situation, so you have this smooth curve and f of a and f of b are the same. In that case, we can always find a point like this or this where the tangent line is horizontal, like this, right? So we have some point between A and B such that f prime of C equals f prime of C is 0. So as I said, that means we have a point C between A and B such that the tangent line is horizontal. There's no up down at point C. Okay, let me correct this. So the tangent line is just horizontal. F prime is 0. In other words, the instantaneous rate of change of the function at C equals 0. We considered one example, and in this example, how do we apply the Rolde theorem? Do you remember that? What was the problem? First of all, we are given this equation, x cubed plus x minus 1 equals 0. And we want to prove that the problem has a solution, has one real solution. And secondly, their solution is exactly one. The solution is unique. So we want to prove the existence corresponding to this have. And then secondly, we want to prove the uniqueness corresponding to exactly one. So we want to consider these two topics. Now, for the uniqueness, we use the intermediate value theorem. So we use the intermediate value theorem. What is it? What does it say? If f of a and f of b or if f of a and f of b are different, then for any value between f of a and f of b, there will be some point in the domain such that the function value equals that given number. I mean, we consider if I have this curve like this, and if f of a and f of b are distinct as in this figure, and if I choose any value like this L, then there will be some point C such that the function value at C equals L. So that is called the intermediate value theorem, and that intermediate value theorem usually shows the existence of a solution. Okay. So that is one of the common usage of intermediate value theorem in calculus. Now, the second part, the exactly one part, for the uniqueness, people usually assume that there are two solutions and then somehow they derive the contradiction, okay, showing, okay, that the assumption having two solutions will be a contradiction, so that there is so that caused a problem, so the solution will be unique. For to derive some contradiction, okay, we use the Rode theorem or mean value theorem. So that is one way of this, the Rode theorem. Rode theorem, okay, or mean value theorem can be used to show the uniqueness of the problem. So as I said, what it did was we assumed that there are two solutions, say A and B. Okay. So when I say two solutions, that means the that points make the function value to zero. So f at A is zero as well as f of B is zero. So if I assume this and I want to derive a contradiction, and people usually use the Rode theorem or mean value theorem. So then how can I use this Rode theorem? Since f of A and f of B are equal, so if I assume that f of A is 0 and f of B is 0, then that means f of A and f of B are equal. Then what does the Rode theorem say? There will be a point C such that f prime at C equals 0. Then why does it cause a problem? Well, given this f of x defined by x cubed plus x minus 1, what is f prime? That is a 3x squared plus 1. Okay? And as we know, 3x squared is always non-negative. But if I add 1, it will be always greater than or equal to 1. So for any x, f prime at that point will be always greater than or equal to 1. Then how can I have a point C whose f prime becomes 0, right? So these two are causing a contradiction. And this contradiction is originated from the assumption that there are two solutions. So the Rode theorem can be used to derive a contradiction from this first assumption. Okay? So that's the usage of the Rode theorem in this problem. Now, today we want to consider the mean value theorem. Before I consider the mean value theorem, please remember that there are three requirements, three hypotheses for the Rode theorem. First, the function is continuous. Secondly, the function is differentiable. And thirdly, f of A and f of B are the same. Okay. Oh, and one more thing. When I say the function is continuous or differentiable, I assumed such continuity or differentiability on certain interval, right? So on the closed interval from A to B, the function is continuous. And differentiability is given on some open interval from A to B. And then f of A and f of B are assumed to be the same. That was the hypothesis of the Rode theorem. Now the mean value theorem eliminates the third one. Okay, so we have the freedom regarding these two function values at these two endpoints. So in case of the mean value theorem, we have only two hypotheses. First, the function is continuous on the closed interval from A to B and differentiable on the open interval from A to B. Oh, and some people neglected this term interval, but please be careful. Okay, I'm considering this continuity or differentiability on single interval, not two separated intervals. Okay, I'm just considering a one single interval, and on that interval, including the endpoints, the function is continuous. And without these endpoints, the function is differentiable on the given open interval. Those are two hypotheses of the mean value theorem. In that case, the claim of the mean value theorem is the following. Previously in the Rode theorem, if I have f of A and f of B are the same, then there is a number C such that f prime of C equals 0. Now, the mean value theorem says that there will be a point C, such that f prime of C equals this. So where did we see this expression? Previously, when I have a function from, say, A to B, then here is f of A and here is f of B. Then the ratio on the right, f of B minus f of A over B minus A. What does it represent? That represents the average rate of change of the function over the interval from A to B. So this value was the average rate of change of this function f over the interval from A to B, or that geometrically that was representing the slope of the secant line between A and B. When I say the secant line, that is representing the line passing through 2 points, okay, of the graph. So A f of A and f of A point and B and f of B point. Given these 2 points, the line passing through those 2 points are called the secant line. And the slope of the secant line was estimated by that expression on the right. So what is the claim say in the mean value theorem? If I have a continuous and differentiable function on certain interval from A to B, then there will be a point C such that f prime C, what does f prime C represents? That is representing the instantaneous rate of change of this function f over the interval from a, oops, sorry, f at point C, or that was geometrically representing the slope of the tangent line at C, right? So these two are the meaning of f prime at C. So, so the claim of the mean value theorem say that we have some C such that f prime is the same as this average rate of change of this function, right? That means we have some point C such that the tangent line has the slope which is the same as the slope of the secant line. That means we have some point C such that this blue tangent line at C is parallel to the secant line. That is the meaning of the mean value theorem. And please note, please remember that this mean value theorem is a generalized version of the Rode theorem, because if if I have the third hypothesis, if f of A and f of B are the same, then what does that mean? Then the numerator of this expression on the right will be 0. And you get the conclusion of the Rode theorem. If f of A and f of B are the same, then there is a point C such that f prime C equals 0. So the Rode theorem was a special case of the mean value theorem, right? So as I said, if you have a function and if f of A and f of B are different, then these blue lines in figure 3 and figure 4 represent the secant lines. And the claim of the mean value theorem is that there will be a point C, at least one C, such that the tangent line is horizontal to the secant line. So we have this line C in figure 3, and there may be more than one such tangent lines which are parallel to the given secant line. There may be, yes, multiple such tangent lines. So that is the meaning of the this mean value theorem. So there will be a point, okay, where tangent line is parallel to the secant line AB. I mean secant line connecting 2 points at A and B. So that is the claim of the mean value theorem. So let us consider a similar example. So let us consider the following function f of x given by x cubed minus x. And let us consider 2 points A and B. A is 0 and B is 2. Now, as we know, this function is a polynomial. So that function is continuous on any interval, and it is differentiable at any real point, right? So if I consider the closed interval between 0 and 2, the function will be definitely continuous on that closed interval. And if I consider the open interval between 0 and 2, the function is differentiable. And the mean value theorem says there will be a point C between 0 and 2 such that f of b, f of b minus f of a over b minus a equals f prime at C. So there will be a point C satisfying this equation. Now, what is f of 2 and what is f of 0? F of 0, if I plug in 0 to the given function, you get 0. So f of 0 is 0. If I plug in 2 to f of x, then 2 to the 3, which is 8 minus 2. So that will be 6. So the mean value theorem says that there will be a point C such that f prime C equals 6 over 2, which is 3. So that is the something. So yeah, right. So f prime C, it will be 3. Now, what is f prime? So f prime is 3x squared minus 1. So 3x squared minus 1 must be 3 at C. So 3c squared minus 1 should be 3. In other words, 3c squared is 4 and c squared is 4/3. So c squared will be 4/3. So c will be plus or minus 2 over square root of 3. The claim of the mean value theorem is that such a C exists between A and B, and the A and B are in this case are 0 and 2. So we are looking for some number between 0 and 2 whose tangent has the slope of the 3. So we just consider between these two numbers, we just need to choose the plus one, the positive value. So the mean value theorem guarantees the existence of such point. And as we observed in the Roger theorem, I mean the example of the Roger theorem, and since the Roger theorem is the special case of the mean value theorem, this mean value theorem is frequently used to prove the existence, the uniqueness of the solution for a certain equation. Okay, so those two are very common examples. I mean, this one and the previous one for the Roger theorem. Those two are common examples of the mean value theorem. Now there is one more example, one more application of the mean value theorem, which is the following. Suppose that f of 0 is -3, okay, and suppose that I have some information that f prime, the derivative of this function, cannot be greater than 5 at all values of x. So suppose that I have such restriction. Then what will be the best, I mean, when I say the best, the largest value of f at 2? So here f of 0 is -3. So I know the one value, okay, which is -3. Then I have one assumption. I have one fact that f prime is bounded by 5. In that case, the question is how large can f of 2 possibly be? So this is one interesting application of the mean value theorem. So if the mean value theorem is, so I know the value at 0 and I want to estimate the function value at 2. So I want to estimate f of 2 and I know the value at 0. So if I consider the mean value theorem, that will be satisfying some equation like this for some C, right? This ratio must be the same as this value for some C, for some C, okay? And I know that this f prime at C is bounded by 5. So this ratio cannot be greater than 5. So here is the expression f of 2 and f of 0 is -3. and 2 minus 0, no, excuse me, this value cannot be greater than 5. So if I multiply 2 to this inequality, f of 2 plus 3 cannot be greater than 10. And then if I subtract 3 from this inequality, f of 2 cannot be greater than 7. Right? So if I use the mean value theorem, I can find the best or the largest value that this function can take. Or sometimes you can find the opposite, the smallest possible value that this function can take. Okay? So to get this maximum or minimum value that certain function can possibly have, you may use the mean value theorem. So the usage of the mean value theorem is to show the uniqueness, right? Or to claim to show the existence of certain point where the tangent line is parallel to the secant line. So to show the existence of such a point, we can apply the mean value theorem. Thirdly, we can find largest possible or the smallest possible value of a function at a certain point, we can apply the mean value theorem. So these three are some common examples of the mean value theorem. And I already explained this. Okay. Now, following theorem and corollary can be proved using the mean value theorem, but I don't want to prove this theorem or corollary, but you need to memorize them. Okay? First, if f prime is 0 on some interval, okay? So in this section, I have certain statement which is described on one interval. This is important, okay? If your function satisfies this, f prime is 0 at all point on one interval, then that function must be a constant on that interval. So this interval is important. And if I have two functions, f and g, and if their derivatives are the same, okay, the derivatives are the same for all x in some interval. Well, if f prime and g prime are equal, then that means f minus g has zero derivative. Then what does the theorem 5 say? If I have such a function, the function must be a constant. So f of x minus g of x, this function before the differentiation must be a constant c. In other words, f of x must be g of x plus c at all points in this interval. Okay, so yeah, I have such a theorem. Please note that if I consider this function f defined by x divided by the absolute value of x, and if x is 0, then the denominator becomes 0, and this f of x in that case cannot be evaluated. So the natural domain of this function will be whole real lines except 0. And if I eliminate this 0, the real line is split into two intervals. So if I eliminate 0, you have your domain consists of two intervals from negative infinity to 0 without this 0 and union 0 to plus infinity. So the domain is the union of two intervals. The domain is not a single domain. And on this domain D, f prime is 0 for all x. F prime is all 0. But f is not a constant function because to the left of 0, the function value is always negative 1. But to the right of 0, the function value is 1. So the graph is 1 to the right of 0, to the right of the y-axis, and negative 1 to the left of the y-axis. So the function is not a constant. It consists of two constants, right? So this is not a constant function. And this does not contradict the theorem because the domain is not a single interval, but it is the union of two intervals. So let me go back to the mean value theorem or the theorem. So the mean value theorem, which is some generalized version of the Roger theorem, say that if you have a function which is continuous on the closed interval, one interval between a and b, and that function is differentiable between a and b. Of course, when I consider the differentiability, the endpoints are excluded. Then there will be a point C between A and B such that f prime at C equals f of B minus f of A over B minus A. In other words, the tangent line at C will be parallel to the secant line between A and B. And this Rolle theorem or mean value theorem focus on a certain property of the function over one interval. That is important. So that is the important property requirement of the mean value theorem. And as I said, there are three common examples of the mean value theorem. First, given certain equation, if you want to prove the uniqueness of the solution, you may use the mean value theorem. Secondly, if you want to find a point C such that the tangent line at that point is parallel to certain secant line, then you may use the mean value theorem. Thirdly, if you want to find the largest possible value of a certain function over an interval, you may use the mean value theorem. So if you happen to have one of those three types of problems, you can try the mean value theorem. Oh, excuse me. Okay. Okay. Now let's go to the next one. Now, we want to consider the meaning of the derivatives in terms of the graph. So what does f prime say about f? I mean, but here we want to focus on the graph. So in this section, what the question is, what does f prime say about the graph of f or certain pattern of f? So to see how the derivative of f can tell us where a function is increasing or decreasing, let us look at figure 1. Between a and b, or between C and D, tangent lines, the red ones, have positive slope, meaning f prime at that point will be all positive. Okay, or mean f prime will be greater than 0. So these, oops, so these tangents have positive slope, meaning f prime there will be all positive greater than 0. Then how about B and C? If we look at tangent lines between B and C, the tangent lines have negative slope. Okay. So between B and C, f prime is negative, and between A and B, f prime is positive, or between C and D, f prime is positive. Now, if between A and B, my function is increasing, and between C and D, my function is also increasing. But between B and C, my function f is decreasing. So between A and B, my function is increasing. And between C and D, my function is also increasing. However, between B and C, my function is decreasing. So what is the conclusion then? Okay, so f prime, when f prime is positive, then my function f is increasing. When f prime is negative, then f will be decreasing. Okay, so whenever you have a positive f prime, if the derivative of function is positive, then the function at that point will be increasing. If we want to find up the interval where the function is decreasing, you need to look for the derivative. If the derivative is negative on certain interval, the function will be decreasing there. So these two go together and these two go together. Please remember this. So here is a test. So if f prime is positive on certain interval, then your function is increasing. And if f prime is negative, then function is decreasing there. Okay? So as an example, given this function f, and I want to find the intervals where this function is increasing, and I also want to find the point, the interval where the function is decreasing. So we start by differentiating f. So if I differentiate f, you get this result. And here 12x is a common term. So if I write down using 12x as a common term, then we get x squared minus x minus 2. And then if I factor this x squared minus x minus 2, you get this product of two first order terms. So we get 12x, x minus 2, and x plus 1. When you have this, okay, what do we want? We want to find the intervals where the function is increasing or decreasing. In other words, so that means, mathematically speaking, that is equivalent to saying that find where this function f is increasing or decreasing. Find the intervals where the function is increasing or decreasing. And that is equivalent to saying that we want to find the intervals where f prime is positive and f prime is negative. So we want to find such intervals, right? Then f prime is a product of three terms, 12x, x minus 2, and x plus 1. Now, if you have such product, then you need to find the points where f prime is 0. F prime is 0 when one of these three terms is 0. 12x is 0 when x is 0. X minus 2 is 0 when x is 2. And x plus 1 is 0 when x is negative 1. So f prime will be 0 at 0, 2, and negative 1. So that is the first step. So step 1, you need to find the points, okay, where this f prime becomes 0. And I can find the 3 points where f prime is 0. The second step, so this is step 1. And step 2, given these 3 points, 0, 2, negative 1, you split the real number line into several pieces, okay, at those 3 points. So step 2, you consider this real number line as in figure 2 and you mark those 3 points, only those 3 points. So negative 1, 0, and 2. Okay. And please remember that we have 12x. That 12x will be negative to the left of 0. So 12x is negative to the left of 0 and positive to the right of 0. And at negative 1, to the left of x, the negative 1, x plus 1 will be negative. And to the right, x plus 1 will be positive. And at 2, to the left of 2, x minus 2 is negative. And to the right, x minus 2 is positive. So we have these 3 situations. Each term behaves a little bit different. So the idea is the first step was to find the the points where f prime is 0. Okay. The second step, you split the interval into several pieces at those points. So at negative 1, 0, and 2. So please remember this negative 1, 0, 2. These 3 points will split the real number line into 4 pieces to the left of negative 1, and then between negative 1 and 0, and then between 0 and 2, and then to the right of 2. So we split the interval into these 4 pieces. Okay? And then on each interval, you just consider the sign of each term. So for example, to the left of negative 1, 12x is negative, x minus 2 is negative, and x plus 1 is negative. Okay? And between negative 1 and 0, 12x is negative, x minus 2 is negative, but x plus 1 is positive. So in this way, you fill this table, okay? And then you generate one more column for f prime, and then you multiply the sign of these three, okay? So minus times minus will be plus, but if you multiply one more minus, you get minus. If you multiply minus, that is plus, and then if you multiply plus, the product will be plus. If you multiply plus with minus, that will be minus. And then if you multiply plus, you get minus. And then if you multiply plus, then the product is product plus. So once you get this sign for f prime, so the step 2 constructs this table. You first split the real number line into these pieces at those points you found from step 1. And then you fill the table. You need to determine the sign, the plus or minus of each term. And then you multiply those signs to determine of f prime of x. And then we get the meaning. Okay, you interpret the meaning of plus or minus. So when you have minus sign, your function is decreasing. If your sign is positive, the function will be increasing. So to the left of -1, the function is decreasing. Let me draw. So -2, 0, I'm sorry, -1, 0, and 2. And to the left of -1, the function will be decreasing. Between -1 and 0, my function will be increasing. Between 0 and 2, function is decreasing. And then to the right of 2, my function is increasing. So this will be some shape of the function, shape of the graph on the whole real line. This is the best one I can do at this point if I have only f prime of x, right? So in a moment we will implement this graph a little bit, but using the f prime of x information, this is the best graph I can generate for f of x, right? To the left of -1, my function is decreasing because f prime is negative. Between -1 and 0, my function is increasing because f prime is positive. Between 0 and 2, my function is decreasing because f prime is negative. And to the right of 2, my function is increasing because f prime is positive. So by looking at this f prime, I can generate, I can have certain feel, okay? Some feeling how probably, okay, if this is the graph of the function, then probably we may guess that probably at -1, at this -1 or n 2, probably my function will have a local minimum. That's what I can guess from this graph. And Probably at 0, my function will have local maximum. So I can find those local minimum or local maximum by looking at this pattern of the graph. And we can easily find those by just estimating the sign, okay, positiveness or negativeness of f prime of x. So I already mentioned this part, and what does the first derivative test say? Suppose that C is a critical number. What was a critical number? Critical number is a point where f prime is 0 or f prime does not exist, right? Now, so if f prime changes from positive to negative, meaning positive to negative, then probably you will have a local maximum there. And at B, if f prime changes from negative to positive at some C, then so then at C, then at that point my function will have a local minimum. But what happens if f prime is positive to the left of C and to the right of C? That means positive to the left and also positive to the right of some point C. Then my function is just increasing, right? So there won't be any local maximum or minimum at C. Or if my function is f prime is negative to the left of C and also negative to the right of C, then my function does not have a local maximum or minimum either. Okay, because in that case, your function is just decreasing near C. Okay, so the first derivative test say that if your f prime changes from positive to negative at a certain point C, then your function has a local maximum at that point. If f prime changes from negative to positive at a certain point, then f has a local minimum at the point. So here's the figure for A. In figure for A, f prime is positive to the left but negative to the right. That means your function changes from increasing function to decreasing function. Then at point C, you have a local maximum. And if your function was decreasing up to the C, and then the function becomes increasing to the right, then you get a local minimum at C. So by just looking at the sign of f prime, we could find local maximum or local minimum. But there may be some situation as in figure 3C or 3D where f prime does not change the sign to the left or to the right of certain point. Say here in C, to the left, f prime is positive. To the right, f prime is also positive. So f prime does not change the sign. In that case, your function is just purely increasing function near C. And in figure 3D, f prime is negative to the left and to the right at C. In that case, your function is purely decreasing function near C. So when you look at around C, your function is just decreasing. So you don't have any local maximum or local minimum at C. Now, okay, we considered f prime. And if I consider f double prime, okay, f double prime is the derivative of f prime. So, so, okay, f double prime is positive, then what does that mean? Then this inner function before differentiation is increasing. So that if the f double prime is positive, then that means f prime is increasing. And f double prime is negative, then f prime is decreasing. This is the result from the first derivative rule, the first derivative test, right? That's what we learned from just moments ago from the previous slide. Now, then, what is the relationship between this statement and f? We are interested in certain pattern of the graph of f itself, not f prime. We are not drawing the graph of f prime. We want to draw the graph of f, not f prime. Then this positiveness of second derivative, what does it say about the pattern of f? So let us consider the following slide. So in figure 6a, my function f is increasing. And in figure 6b, my function g is also increasing. So these two functions are increasing between a and b. Then what's the difference? The shapes are different, right? Now then, is it related with f prime? What is the slope? Slope is like this. Then what does then, so between a and b on the left in figure 6a, the slope is increasing. Please note that the slope is increasing. But in figure 6b, D or C, the tangent line is very steep, meaning the large slope. But that slope becomes smaller and smaller, right? So that means the slope is decreasing. Okay, so please remember that both functions are increasing. Okay, these are increasing functions, but the increasing pattern is different. In 6a, the slope, and slope, in other words, is f prime. F prime is increasing. That means, as I said here, if f prime is increasing, then that means f double prime is positive. F prime is decreasing, then f double prime is negative. So this portion implies that f double prime is positive. Then your function increases as in figure 6a. If f double prime is negative, then the slope is decreasing as in figure 6b. So what I usually do personally is this. Since these, first derivative or second derivative, these are a little bit confusing. what I usually memorize myself is to consider x squared function and negative x squared function. If you draw the x squared function to the right of 0, the x squared function is increasing, and the increasing pattern is very similar to that of figure 6a. And in case of negative x squared, the increasing pattern to the left of 0 of this negative x squared is very similar to that of figure 6b. And in case of x squared, f double prime is positive to the right of 0, and f, when negative x squared is considered, f double prime of x is negative, oops, yeah, negative to the left of 0. So on this interval, f prime is positive. On this interval, f prime is positive. So f prime is positive and f double prime is positive. Then the increasing pattern will be like this. When I consider negative x squared function to the left of 0, f prime is positive, but f double prime is negative. So that's what I do for this case. How I remember the shape of the pattern. Okay, so let me explain this one more time. So if you think of the x squared function, f prime of x is 2x, and this function is increasing for x greater than 0, and on that interval, if I consider the second derivative, it is 2, which is positive. So for the graph of x squared, I look at the portion corresponding to positive x. So on this interval, my function is increasing, okay, and the increasing pattern is like this. In case of the negative x squared function, f prime of x is negative 2x, and that is positive for negative x, and f double prime of x is negative 2, which is negative. So since f prime is positive, my function is still increasing. Then increasing pattern is like this. To the left of 0. Okay. And whenever you have certain function f, and f prime is positive and f double prime is also positive, then the increasing pattern will be like this. Okay. If f prime is positive but f double prime is negative, then the increasing pattern will be like this on the right. So that's what I personally use. I always think of x squared and negative x squared and just compare the pattern. And if you have the increasing pattern as in figure 7a, we say we say the function or the curve is concave upward. And if your function increases as in figure 7b, then we say the curve is concave downward. Okay, so concave upward or concave downward. But as I said, you may consider x squared and negative x squared function to get the pattern. Okay. So then, then what is the definition of being concave upward or concave downward? So in figure 7a, I said the curve is concave upward. That means it is concave upward if when you draw the tangent line, your graph is above the tangent line on that interval. Okay? In that case, we say the curve is concave upward. So, so if your curve lies above the tangent line, then we say the curve is concave upward. In case of figure 7b, whenever you draw any tangent, your graph lies below the tangent, then we say the curve is concave downward. Okay? So f double prime is a negative, then the tangent line and the curve lies okay below the tangent. In that case, we say the curve is concave downward. If f double prime is positive, so that between tangent and curve, if curve is above the tangent, then we say concave upward. So upward curve is greater than tangent and f double prime is positive. Okay. And downward f double prime is negative. So okay, let me change this order. That might be easier to memorize. So f double prime is greater than 0, curve is above the tangent and upward, okay? So they go as one team. F double prime is negative, so that curve is below the tangent. Then you get concave downward. They go as one team. Now, if the graph of f lies above all of its tangents on certain interval, then we say the function is concave upward. So it is, if the tangents are above the tangent, then we say the function is concave upward. If the graph of f lies below the tangents, then we say f is concave downward. Now, moments ago, I mentioned that the graph of x squared and negative x squared can be used, right? Whenever you see the pattern of x squared shape, decreasing or increasing, it is called concave upward. If you see the pattern as in y equals negative x squared, concave downward. So this is decreasing, and here is an increasing part. F prime, the increasing or decreasing doesn't matter. As long as the graph looks like that of x squared, then you get concave upward. If you see increasing or decreasing, but if you see certain pattern as in negative x squared, then the curve will be concave downward. So in the figure 8, between A and B, the graph look like, so up to this, that is similar to the negative x squared graph. And then you see the pattern like this, so that between A and B, your graph is concave downward. And then between B and C, the graph first decreases and then increases. So between B and C, the graph looks like that of y equals x squared graph. So your function is concave upward. Now between C and D, your function is increasing, but the increasing pattern looks similar to the increasing of negative x squared function. So your function is concave downward there. And then between D and E, my function first decreases similarly to the x squared function, and then it increases. So between D and E, the graph looks like y equals x squared function. So the graph is concave upward. And then between E and P, my function is purely decreasing, and the decreasing pattern is that of y equals to x squared function. So it is also concave upward. And then between P and Q, my function decreases, and the decreasing pattern is now similar to that of y equals negative x squared function. So yeah, so that will be concave downward. So if you can, I mean, you can always think of a certain tangent, okay, and then you can compare the location of the tangent line and the actual graph. And if the actual graph is above the tangent line on certain interval, your function will be concave upward. And if your graph is below the tangent, then it will be concave downward. Okay, but it was confusing to me. So that's why I personally memorize x squared and negative x squared. And if your function has a similar shape as in x squared function, your graph is concave upward. If the graph looks like that of a negative x squared graph, then it is called concave downward. So moments ago, we considered the increasing pattern, two increasing pattern, the increasing but concave upward and increasing but concave downward, right? So that was the case to the right of x squared part and to the left of negative x squared part. And similarly, if I consider the left hand side of 0 of x squared, your function is decreasing, and the to the right of 0 of negative x squared function, the graph is decreasing. So you get two decreasing functions, but these decreasing patterns are different, right? So you may rely on the relative location between the actual graph and the tangent line, or you may consider this graph of y equals x squared or negative x squared as I did. Okay, but anyway, let's take a break and then let us resume in 15 minutes. Okay, thank you for listening and see you in 15 minutes.